Hello, math study students, and welcome to outer space. We're in outer space now because we're getting out there, man, with some crazy maths. If you're up to speed on recent work, then you've done some work with limits. We've talked about famous mathematicians of a pretty exciting time in math. And in particular, the discovery slash invention of Gottfried Leibniz and Isaac Newton working independently of each other. Though it is true that Leibniz wrote Newton wrote a letter and asked some question, and Newton told him something, and that was prior to Leibniz doing his work to figuring out this particular branch of math. But anyway, we're going to talk about calculus. Yes, indeed. Now, there's a couple of branches of this, but the one we're going to talk about to start off is something called differential calculus. And in differential calculus, we spend a lot of time talking about something called a derivative. Now, derivative, the root word there is to derive something. And the basic concept of this, quite frankly, this is a subject in math that I think should be taught probably in 8th grade, honestly, maybe even before that. Because whenever you start learning linear functions and learn y equals mx plus b and learning about slope, what you do learn is that lines have slopes and the slope is the same all over the place. So if you have a line that's sloping up, it's got a positive slope, and if it goes down, it's got a negative slope. Well, as it turns out, slope isn't reserved just for lines. Curvy functions can also have slopes. So if you have some kind of an exponential function that's going along and then taking off somewhere, that is, like if you had 2 to the x, for example, so 0 it equals 1, and then it equals 2, then 4, then 8, then 16, and takes off really fast. So actually that's going to look, like that. You'll find that over there in the second quadrant, that thing is very flat. And as you go up, it becomes very, very, very steep. And if you think about the idea of limits, the limit of that slope as you go to negative infinity would be 0. The thing gets really, really flat. And the limit as you go up there is that it's going to be so steep, it gets to be infinitely steep. If you take a look at a parabola, and we're going to do that in a moment over here by the spaceship, we're going to put y equals x squared. You'll find that in the first quadrant, y equals x squared has a positive slope. In the second quadrant, has a negative slope. At the origin, it's horizontal and the slope is 0. If you look at the parent cubic function, y equals x cubed, that thing comes up from the third quadrant, levels off, and then shoots up into the first quadrant. And that slope is 0 right there, and up it goes. And that's what x cubed looks like. So it's always got a positive slope, except for when the slope is 0. And its slope is small near the origin, and its slope is much bigger as you get further away. If you look at how a sine curve looks, the sine curve goes up and down and up and down and up, and so does cosine. That's got slopes that are positive, then negative, then 0, and positive, and negative, and 0. You can go around a circle and start talking about the slope. It can be horizontal at the top and bottom, undefined, or vertical at the edges. And there it can have positive and negative slopes in different places. So all sorts of things have slopes. It's just that at different points, those slopes are different things. So to talk about a derivative, over here by the spaceship, we're going to cover it up. See you guys. And put y equals x squared in here and talk about this fact. If you look at the slope of this function, which is just going to be, you put a line up against it, how steep is that line? That when you're way up there in the first quadrant, it's very steep. As you start, well, let's do this. Go way up there in the second quadrant when it's very negative. And then start working your way down. I should get out of the way of there. When you start working your way down, it gets horizontal. Then it starts to go positive and gets more and more positive as it goes along. So there isn't some random pattern here between the slope and x. There's some very clear pattern. And the insight that Leibniz and Newton had was that it is possible to build from y equals x squared a new function, which will be the function that tells you the slope of that other function. So if we call our original function f of x, the notation we're going to use right now is f prime of x. That's going to be the derivative of f of x. And we call it a derivative because it's derived from it. What I'm going to have you guys do is do your first little bit of differential calculus, because you are going to derive a slope function from y equals x squared. I'm going to tell you how to do it, so you can get a notebook and start trying to get this stuff down, then take a picture of what you've done and send it in. We're going to actually do 2 of them, and it's pretty exciting. So we're going to deal with this y equals x squared. And the question is, what is the function that tells you the slope of the function y equals x squared? Now, how we're going to do that is this. Slope is just rise over run, right? And another way of thinking about that is delta y over delta x. Make sure you understand that notation, what that actually means. Why rise over run is the same as delta y over delta x. Now that delta y, we're going to break that down into the idea of a y2 minus y1. Where we're going to get our y2 is we're going to start with an x, and then we're going to add a little bit to it. And that little bit is going to be a delta x. So we have x plus delta x. We're going to square the whole thing. That's going to give us our y2. Minus y1, we just subtract x squared. So we have x plus delta x, the quantity squared, minus x squared. Now remember not to do the freshman dream. Remember that this x plus delta x, the quantity squared, is going to have 3 terms in it. And the second row of Pascal's triangle, the 1, 2, 1 row, will give you the coefficients for those terms. Okay? When you do the subtraction problem and then do the division problem, you'll have your delta y over delta x. For that, you'll have your derivative. So do that work, see what cancels, see what you get. Here's the second one. The second one is not y equals x squared. It's going to be, and goodbye guys, it's going to be, or hello again to the say hello to the astronauts that are apparently orbiting Saturn very, very slowly because they're not moving at all while we're here. They're paused, waiting. They'll fire up the rockets and get going soon. See their solar panels? They're being very efficient. Anyway, the other function is going to be the parent cubic, y equals x cubed. And so once you do a x plus delta x, the quantity cubed, minus x cubed all over delta x, and see what you get for that. Okay? After doing that one, if you notice some kind of a pattern between those, you can answer a third question, which is, what do you notice? Because maybe you'll notice something. To help you out real quick with that cubic, the third row of Pascal's triangle, the 1, 3, 3, 1 row, x plus delta x, the quantity cubed. You can work it out on your own if you like. So you can just go, I'm not listening right now. But anyone else that wants to hear it, x plus delta x, the quantity cubed, is going to be x cubed plus x squared delta x. Oh, I'm wrong. Oh, ignore that. It's going to be x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. Then subtract the x cubed, because that's the y1 that you subtract from that big long y2 to get your delta y, all over delta x. When you do that division problem, see how the delta x's cancel it, what you get. Okay? That's about it. That's enough for now. So have a good time working on that one, and welcome to differential calculus. Hope you enjoy it. Thanks. Bye-bye.